Section 9.3, double angle, half angle, and reduction formulas. So the next set of trig formulas that we're going to look at, or trig identities, are the double angle formulas. And we finished the previous section by deriving cosine 2x, the formula for cosine 2x, using the sum formula for cosine, just applied to an input of x plus x. All right, and we found these three equivalent expressions right here. We also have double angle formulas for sine and tangent. For sine 2x is equal to 2 sine x cos x, and tangent 2x is equal to 2 tangent x over 1 minus tangent squared x. You might be able to imagine how this one is derived from the sum formula for tangent. Just to, find tangent of x plus x and apply the formula. You might be able to imagine how that formula would pop out. Okay, let's try example 1 applying these formulas. We're told that sine of x is equal to root 2 over 3, and x is between pi over 2 and pi. So really what I'm thinking when I see this is that x is an angle that is in quadrant 2. So I'll just make a note of that real quick. X is in quadrant 2. And we're asked to find cosine of 2x, sine of 2x, tangent of 2x. So we'll definitely be using these formulas here at the top of the page. And there's a bit of a trick here, and we've used this trick recently in the past, where we can solve these types of problems without ever actually finding the value for x. And I hope that we can achieve that, because root 2 over 3, this isn't really an output that I'm used to seeing, so I suspect that x isn't one of those friendly angles like pi over 3 or pi over 2 or pi over 4 or something like that. So here's the trick to this problem, and I'll write this out. The trick is that by using double angle formulas, we can find cosine 2x, sine 2x, and so on. Without ever having to find x. And we've used this strategy before with the Pythagorean identity. Like, there have been times where we've been given problems similar to this and been asked to find cosine x, and we saw that we could just apply sine squared x plus cosine squared x equals 1. Substitute in what we have for sine, this root 2 over 3, and solve for cosine. We're going to do pretty much the same thing here, except we're using the double angle formulas. Okay? So just a couple things to sketch out before we really get started. I just want to show, this angle x is somewhere in quadrant 2. Right, so I don't know exactly what this angle is going to look like, but I know that it's going to be over here. Okay, and we want to bear in mind all students take calculus. Sine is going to be positive in quadrant 2, but that won't be the case for cosine or tangent. Okay, so when we go, how about we start with cosine 2x? That's the first one we're asked for. So cosine 2x, let's try to find this. I'm going to start with the formula. Notice that we have a few different formulas. We have cosine squared minus sine squared. We have 1 minus 2 sine squared, 2 cosine squared minus 1. I have my pick here. I'm going to use that second one, 1 minus 2 sine squared x, because I have a value for sine of x, right? I know sine of x is equal to root 2 over 3. So now I can substitute in 1 minus 2, and then I'll substitute in root 2 over 3 for sine x. And I'll simplify a little bit. This is 1 minus 2 times, so squaring the numerator and denominator, I'll just get 2 over 9. So I get 1 minus 4/9. And just taking that difference, I could get common denominators, write 1 as 9 over 9. And I see that I get 5/9 as my output for cosine 2x. Okay, so looking at this 5/9, you might be thinking, wait a minute, this was a cosine. I was expecting to get a negative value here, right? Because all students take calculus. X is in quadrant 2. Why did I get a positive 5/9? Well, we aren't finding cosine of x. We're finding cosine of 2x. So if this is the angle x, 2x could be in either this quadrant down here, right, in quadrant 3, or it could be in quadrant 4. Okay, and what this just told us is that 2x is in quadrant 4. Okay, so this positive 5/9 is acceptable because we're not finding cosine of x, we're finding cosine of 2x. Let's keep going. How about, let's see, we want to find sine of 2x. So let's do that down here. Sine of 2x. The formula for this one is 2 sine x cos x, like that. All right. So this one, I can substitute in what I have for sine. I know that that is root 2 over 3. But cosine x, I don't know what cosine x is. I know what cosine 2x is, that's over here. I'm sorry, we can't just divide that by 2 and get cosine x. That's not how this works. We're going to have to use the Pythagorean identity to find cosine of x. Okay, so I'll say here first, we need to use the Pythagorean identity to find cosine of x. Okay, so here's our Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. Sorry, this is just a little arrow here. Okay, I know that sine is root 2 over 3, so I can substitute that in. We've done this before. And I could simplify, I could solve for cosine, and here's what I get when I solve for cosine x. I'll get, and you know, it's going to be a plus or minus square root of 1 minus 2 over 9. All right, which just simplifies to the square root of 7 over 9. Or, you know, just plus or minus root 7 over 3. We could simplify it like that. All right, now, which is it, plus or minus? Here's where all students take calculus does affect the sign, because we're just finding cosine of x right now. So we really are looking at this angle in quadrant 2. So quadrant 2, that tells us that cosine is negative for this angle x. So I'll go ahead and substitute this in. It's actually going to be negative. It'll be negative root 7 over 3. Okay, and that negative right there is because of all students take calculus. Remember, this angle x is between pi over 2 and pi. Okay, now, keep working over here. I can say that sine 2x will be equal to 2 times sine of x, which is root 2 over 3, times cosine of x, which is negative root 7 over 3. And let's simplify this down. I can write this as negative 2 root 14 over 9. And that will be our answer for that. All right, and we're almost done. Now we just have to find tangent of 2x. All right, and we could use the formula here, but remember, tangent of 2x is the same as sine 2x over cosine of 2x. So rather than turning to the formula and doing all that, I'm just going to take the quotient of these two values that I've found. So it will be sine of 2x, which is negative 2 root 14 over 9 over, or divided by 5 over 9. And I'll multiply by the reciprocal. So times 9 over 5. The 9's cancel out, and tangent 2x will be equal to negative 2 root 14 divided by 5. Okay, so we were able to evaluate cosine 2x, sine 2x, tangent 2x just by using those formulas and that technique of sort of avoiding finding the value of x by just employing some trig identities. That's a fantastic problem to study from. You'll see problems like it on homework and in class. Let's keep moving to example 2. We want to verify this identity. We've got that allegedly sine squared theta minus 1 quantity squared is equal to cosine 2 theta plus sine to the 4th. Now, verifying identities, one of our common strategies that we use is start with one side. Sometimes the more complicated looking side is better to start with. See if you could simplify, use algebra, apply some identities, just to do what you can, and see if you can get it to look like the other side of the equation. Okay, so looking at these two sides, trying to size them up, if I started on this side of the equation, I might try multiplying it out, like foiling that out and seeing if I can get something for a cosine 2 theta to pop out, looking at the formulas for cosine 2 theta. So I could start with the left-hand side and start by multiplying it out. I could start by the right-hand side and, maybe substitute something in for cosine 2 theta since I have 3 options for that. So I think either of those approaches could be viable. I'm going to start with the left-hand side, which is sine squared theta minus 1 squared. Because, okay, this is the same as sine squared theta minus 1 times sine squared theta minus 1, right? I do not want to see people taking this second power and just applying it to each of those. You know, we can't do the distributive property with exponents. We have to FOIL it out like this, or box method, you know, however you like to multiply these things out. So now multiplying these together, I'm going to do first, outer, inner, last. So multiplying the first two terms together, I get sine to the fourth theta. Kind of happy to see that sine to the fourth theta, since I'm going to need that to get to the right hand side. And then it'll be, okay, outer minus sine squared theta, inner minus sine squared theta, and then plus 1. That's multiplying -1 times -1. And I can simplify a little bit. Sine to the fourth theta minus 2 sine squared theta plus 1. Okay, I have my sine to the fourth theta, right? Like there it is right there. Now I just am trying to figure out how can I get cosine 2 theta to pop up. And I have this. If I look up to my double angle formulas, this second formula, 1 minus 2 sine squared theta is equal to cosine 2 theta. And I have something that looks pretty much just like that. I'm just going to rearrange these terms. Addition is commutative, meaning I can rearrange terms however I like. If I rewrite it like this, I see that this is equal to cosine 2 theta. Oh, sorry, I just wrote 4 there. I meant to write sine to the fourth theta. And that term remains as well. And would you look at that? That is the right hand side. So we did it. The identity is verified. I'll do my little proof box. It's confirmed. Okay, if you had started on the right-hand side, you would have started by applying that double angle formula right there for cosine 2 theta, and then you would have factored, which, you know, if you're good at factoring and sort of recognize that this expression is quadratic in form, you could have done that. I just decided to start by multiplying it out. I think it's a little more obvious if you start on that side, okay? But you could totally start with the right-hand side as well. Okay, how about example 5 here? Okay, for this one, we want to verify that sine of 3x is equal to 3 sine cosine squared x minus sine cubed x. Well, this looks like the more complicated side, so traditionally we might try to start there. But this sine 3x is very strange. We have seen sine of x, we have seen sine of 2x, like we have double angle formula. This is technically a triple angle, and we don't have, you know, a formula for sine of 3x. So while it's tempting to start messing around with the more complicated side, I think that I might start on the left-hand side here and see if I can do something about this sine 3x. So left-hand side is equal to sine 3x. And that factor of 3, we really are stuck with that on the inside of the sine function. Like we can't bring that 3 to the outside magically or anything like that. So how are we going to adapt or maybe break up that 3x so that we can apply some formulas that we do have? We don't have triple angle formula, but we have double angle formula. We also have the sum formula for sine. And I'm thinking that might be helpful because, you know, the way that we originally derived the double angle formula is by using the sum formula. So maybe we could do something like this. I could write this as sine of x plus 2x, right? X plus 2x is equal to 3x. And now that I have a sum inside of the sine, you know, as the input for our sine function, I can use the double angle, or excuse me, the sum formula to break this up like this. It'll be sine of x cosine 2x plus cosine x sine of 2x. Okay, and I'm aiming for this up here. I'm not seeing any similarities so far, but I'm going to just be persistent here and see what happens. The second term, sine 2x, I'm going to replace that sine 2x with the one formula that we have for sine 2x. This will just become cosine x times 2 sine x cosine x. And for this one, cosine 2x is always tricky because we have 3 options to substitute in for cosine 2x. And I don't know, I'm trying to get a sine cubed x. So here, if I scroll up just to show you what our 3 options are, here they are. Given that I'm trying to get a sine cubed x, I think I'm going to use either option 1 or option 2 because there's sine squared x's in there, and I know that I'm multiplying this by sine of x, so that would get me there. Now, which one do I want to use? Do I want to use the first one or the second one? Well, if I use the first one, and again, I am totally just guessing here. I'm just going to try. If I use the first one, cosine squared x minus sine squared x, when I, in the next step, distribute, so I'll distribute this sine, oh sorry, that should say sine of x right there. When I distribute this sine x to these 2 terms, I'll get sine x cosine squared x minus sine cubed x. So that's good, that's the sine cubed x that I was trying to get. Let's see how the rest of this works out though. So now multiplying these together, this will be 2 sine x cosine squared x. Just multiplying in that factor of cosine x. And okay, so I have my sine cubed x. Now I'm trying to get this 3 sine x cosine squared x. And actually I think this is working out because there's sine x cosine squared x, there's sine x cosine squared x. If this is 1 sine x cosine squared x and this is 2, if I add those together, I will get 3 sine x cosine squared x. And then I'll still have that term, negative sine cubed x. So we made it. That is the right hand side. So we've verified this identity. The right side and left side are truly equal to one another, no matter what the input x is. Okay, so just a couple, verifying identities. Now we'll have more formulas and identities to pull from when working on these problems. How about example 6? Sine of 2 sine inverse of 4 over 5. Back in chapter 8, when we were dealing with inverse functions, we saw a lot of different examples where we would have a function, a trig function, composed with either its inverse or, maybe a trig function composed with an inverse of another trig function. And what we usually would rely on is, we usually would let theta equal whatever the inverse value is. So we would let theta equal, in this case, sine inverse 4 over 5. So then we would know, okay, sine of theta is equal to 4 over 5. Okay, that would be part of it. And we'd also usually use a Pythagorean identity to try and evaluate a trig function without having to find theta. That's sort of been the common strategy here. Now the curveball for this one is this factor of 2. We have a factor of 2 being multiplied by the interior function. All right, so this is going to be a double angle formula. But I'll start the way that we normally would. Let's start by saying, let's let theta equal sine inverse 4/5. Okay, so then we can take this over here and I can rewrite this as sine of 2 theta, like this. And now we just have a double angle, so to get out of that predicament, we could rewrite this as 2 times sine theta cosine theta, like this. And now we just have to evaluate what is sine of theta, what is cosine of theta. Okay, well, remember, over here, sine of theta must be equal to 4/5. Okay, and this is where theta is between -pi/2 and pi/2. This is the right half of the unit circle. Remember, the output values for inverse sine functions always are in that right half of the unit circle. Okay, so I know what sine is, right? So like over here, I know this is going to be 2 times 4/5 in for sine, but what about cosine? Okay, so we're going to have to find what is cosine of theta. Okay, so now over here, let's find cosine of theta. And we will use the Pythagorean identity to do that, just like we have in previous examples. Sine squared theta plus cosine squared theta is equal to 1. Sine, I know, is 4/5. Substitute that in. So then cosine theta is going to be plus or minus the square root of 1, or here, I'm going too fast here. Let's leave this as cosine squared theta, and then I'll have 1 minus 4/5 squared, which is just 16/25. So cosine squared theta, I could think of 1 as 25/25, so I get 9/25. Okay, and then take the square root of both sides. Cosine theta is equal to plus or minus square root of 9/25. And those are both perfect squares, so I just get 3/5. Now, which is it? Is it positive or negative? Well, remember, this angle theta is somewhere on the right half of the unit circle. Okay, so it's somewhere over here. And all students take calculus. If it's in the right half of the unit circle, cosine is going to be positive no matter what, right? Because in the first quadrant, all the trig sine, cosine, tangent are all positive. And in the fourth quadrant, cosine is positive. So this is going to be positive. All right, and then now bringing this up here, I can substitute in for cosine. I have positive 3/5. And now I can just simplify. I think I'll get 24/25, multiplying those three values together, and that is my answer. If you want to see more similar examples, look back to section 8.3. We do quite a few that are like this. This just has the curveball of having to use that double angle formula in the first step. Okay, half angle formulas. These are the next ones. If we take cosine 2x and 1 minus 2 sine squared x is one of them, one of the formulas for cosine 2x. The other one is 2 cosine squared x minus 1. If we solve for cosine squared x and sine squared x in each of those, we get half angle formulas. Okay, and there are a couple different ways of expressing these. So this one, cosine squared x over 2 is equal to 1/2 times 1 plus cosine x. You know, we have one for sine squared x over 2, tangent squared x over 2. Notice that there are kind of two things going on here. We have that cosine is squared, and we also have that the angle is being divided in half. So we could express these formulas this way. Another way we could express them is taking the square root of both sides. We get cosine x over 2 is equal to plus or minus square root of 1/2 times 1 plus times 1 plus cosine, or you could write it as 1 plus cosine x over 2, like this. We can do the same for sine. We could write this as sine of x over 2 equals plus or minus the square root of 1 minus cosine x over 2, and tangent x over 2 is equal to plus or minus square root of 1 minus cosine x over 1 plus cosine x. And you could probably observe that this right here, this formula for tangent x over 2, is just sine x over 2 divided by cosine x over 2. That's how we derive that one. Okay, so a couple different versions of the same formulas. Let's see how we would apply these in example 7. We want to evaluate cosine of pi over 8. Okay, so we're evaluating cosine at an angle that is not one of our favorite angles. You know, it's not pi over 6, pi over 4, or pi over 3, or pi over 2. It's not any of those friendly values. Pi over 8 is just a little too small. And the half angle formulas come in handy when you have an input that just seems a little too small. Like if we could double this, you know, if we were dealing with pi over 4, that'd be much easier to work with. So what I'm going to do is I'm going to rewrite this as cosine of, and I'm thinking pi over 8 is half of what angle? It's half of pi over 4. So this is like pi over 4 divided by 2. So pi over 4 is going to be like our x in the formula. All right, so this is why we call them the half angle formulas. We're going to express this input pi over 8 as half of some other angle. Now, I can evaluate this by using this first formula up here. Right, so this will be equal to plus or minus the square root of 1 plus cosine pi over 4 divided by 2. Okay, and how about the plus or minus? We could deal with that right away. Cosine of pi over 8 is going to be right over here. You know, it's going to be this very slender angle right here. This is in quadrant 1. So all students take calculus. Is this going to be positive or negative? It's going to be positive. All right, and now that we have rewritten this in terms of a nicer angle, I know what cosine of pi over 4 is, so I'll substitute that in. This is going to be the square root of 1 plus root 2 over 2. Sorry, I'm writing kind of small there. And this whole thing is divided by 2. And now I just have to simplify. I can write 1 as 2 over 2, so I'll have 2 plus root 2 over 2, like that. And the big fraction bar is right here, and we're dividing by 2. So I can multiply by the reciprocal of 2. This becomes the square root of 2 plus root 2 divided by 2 times 1/2. All right, so I'll end up with 4 in the denominator. And last thing I'll do to simplify is I can do square root of 2 plus root 2 divided by 2, like that. And I will box it up. Okay, and for your homework, you'll likely be typing in something like this for certain problems. So be prepared to deal with these sort of nested radicals. Just be careful with your parentheses and everything and how you're entering this in to Canvas homework. Okay, but that's our process, right? Express whatever this angle is as half of some other angle, and then that other angle is what we get to work with in the formula. Use all students take calculus to determine whether it is a plus or a minus. That'll depend on which quadrant this angle falls in. And then from there, just carefully simplifying. We've got one more of these, sine of 15 degrees. So we're in terms of degrees here. 15 degrees is not an angle that I'm super comfortable working with or super familiar with. However, this is half of 30. So I could write this as sine of 30 degrees divided by 2, like that. And this is good because I can then use the half angle formula. So plus or minus square root of 1. This one is minus cosine x. And we're working with 30 degrees now, divided by 2. Is it plus or minus? Well, 15 degrees is in the first quadrant, so all students take calculus, so this will be positive. All right, and I get the square root of 1 minus cosine of 30 degrees. So here we can, how about we do a triangle this time? Here's our 30-degree angle. This is a 30, 60, 90 triangle, so I know it has short side is 1, hypotenuse is 2, long side is root 3. Cosine is adjacent over hypotenuse, so it'll be root 3 over 2. And this is all divided by 2. And now we get to simplify. It's going to look pretty similar to what happened in the previous example. This will be 2 minus root 3 over 2, and then that's the numerator, and then main fraction bar, whole thing's divided by 2. Okay, and what we'll end up with is square root of 2 minus root 3 divided by 2, like that. Okay, because we get the 4 in the denominator inside of the radical, and that just, square root of 4 is 2. So another interesting kind of nested square root type answer for that one. Example 9, if sine of alpha, this is just the first, lowercase first letter in the Greek alphabet, sine of alpha is equal to negative 4 over 5, and alpha lies in the fourth quadrant. Find cosine of alpha over 2. All right, sine of alpha is negative 4 over 5, and we know that we're in the fourth quadrant, right? So this angle alpha is somewhere down here. I don't know where exactly. I'm just drawing it out. Okay, all students take calculus. So, sine is negative in this region, so that tracks. Okay, and we want to use a half angle formula, obviously, because we're trying to find cosine of alpha over 2. So just to write that out, like what is the formula here? Well, cosine of alpha over 2 is going to be plus or minus square root of 1 plus cosine alpha over 2, like that. So I will need cosine alpha in order to figure this out. So step 1 is going to be, let's find cosine of alpha, given that sine of alpha is negative 5/4 and alpha is in the 4th quadrant. So let's find cosine alpha. And you know the way we do this, we use the Pythagorean identity. Sine squared alpha plus cosine squared alpha is equal to 1. Sine squared alpha, I'm going to substitute in negative 4/5 for sine alpha. Okay, so then cosine squared alpha will be 1 minus negative 4/5 squared, which I'll just put in is 16 over 25. So I'm getting cosine squared alpha is 9 over 25. So cosine of alpha is plus or minus the square root of that, which is 3 over 5. Which is it plus or minus? Well, we're in the 4th quadrant. Alpha is in the 4th quadrant. Cosine is positive in that quadrant. So we are actually going to have a positive output for that. All right, so that's just a bit of scratch work, really. So now over here, we want to plug into this formula. Before we do that, let's talk quickly, plus or minus, right? Is this going to be plus or minus positive or negative output for cosine alpha over 2? So I want to make a note here. So note, alpha is in the 4th quadrant, right? So the 4th quadrant goes from 3 pi over 2 to 2 pi. Okay, so if we want to determine like what is the sign of cosine of alpha over 2, we need to know where alpha over 2 falls on the unit circle. What we'll do is we'll divide all 3 sides of this inequality, this compound inequality, by 2, right? So I could do, times 1/2 here, times 1/2 here. I can divide by 2 in the middle. Okay, and then I'll get 3 pi over 4 is less than or equal to alpha over 2, which is less than or equal to pi. Three pi over 4 and pi, somewhere between 3 pi over 4 and pi. So looking back over here, our unit circle is here. 3 pi over 4 and pi, let's see, I need a new color. How about, let's do yellow. 3 pi over 4 is right there. Pi is right here. Okay, so just making a note of this picture, I'll say alpha over 2 is in here somewhere. Highlight this little region here. So then the question is, cosine of alpha over 2, is it going to be positive or negative? Well, we fall in the 2nd quadrant then. Sine is positive in the 2nd quadrant, cosine is negative. Okay. So from this we can determine, so then alpha is in quadrant 2. Thus, cosine of alpha, or sorry, this should say alpha over 2 is in quadrant 2. So cosine of alpha over 2 is going to be equal to negative square root of 1 plus cosine alpha over 2. And we have a value for cosine alpha. We got 3/5. So 1 plus positive 3/5 over 2. Okay, getting common denominators in the numerator of the big fraction. I'll write 1 as 5 over 5, so I'm going to get 8 over 5 up here. Okay, so my final answer will be negative square root of 8 over 10, like that. Or if you want to rationalize the denominator, it would be negative root 80 over 10. All right, so this problem had that additional little bit of analysis here where to determine whether this is positive or negative, we had to think about alpha over 2. If we're given some restriction on alpha, we can determine what the restriction is on alpha over 2. Use all students take calculus to determine the sign of cosine of alpha over 2. Oh, and actually, this radical can simplify a little bit. There's a factor of 16 and 80. So I could write this as negative 4 root 5 over 10, which would simplify a little bit more to negative 2 root 5 over 5, like that. So apologies, I forgot to simplify this radical. Square root of 80 had that factor of 16 in there, so I pulled that out. And now looking at example 10, last example from this section, we've got an identity that we want to verify here, and we're sort of tipped off. Half-angle formulas are going to be involved. And here's what we're trying to show. We want to show that sine cubed 2x is equal to 1/2 sine 2x times 1 minus cosine 4x. Okay, and looking at both sides, again, just seeing if I can recognize anything, any path forward. We could start with this more complicated side. And something that's sort of standing out to me on the right-hand side is I see this 1/2 1 minus cosine 4x, which looks an awful lot like the half-angle formula for sine. Okay, and then there's also this factor of sine 2x hanging out over here. Okay, and then on the other side of the equation, I see we have sine cubed 2x. Another thing that I could try, and this is just me sketching out some ideas, I haven't committed to anything yet. But on this side, like, if I write sine 2x times sine squared 2x, like that. See how, I could apply a half-angle formula right here to this. Okay, so I'm just sort of sketching out some ideas and trying to decide on my direction here. So, you know what, maybe I'll start with the left-hand side and kind of aim for that, 1/2 1 minus cosine 4x. Hopefully that pops out of the half-angle formula. So I'm gonna try this. This isn't the only way to do it, but this is what I'll do. Let's start with the left-hand side. And I'm gonna start with sine cubed 2x. And I'm going to use that strategy that I just mentioned. I'm going to break this up to sine 2x times sine squared 2x like this. Okay, and you know, this makes it look like I already have the sine 2x part handled. All right, so if we want to apply the half angle formula to that sine squared 2x, I want to write the inside, this 2x as something over 2. All right, so that would be sine 4x over 2, like this. Okay, and the way that another way to think about that, or like how I got that, is basically multiply top and bottom of that number on the inside, 2x. Multiply top and bottom by 2. Like that. Okay, and I have to do that because if we scroll back up and look at the formulas, this is the formula that I'm shooting for right here. And I need to have that x over 2 happening on the inside. Okay, but that's a good thing because the 4x pops up, which sort of justifies this 4x over here on the right-hand side of the identity. So I feel like I'm heading in the right direction here. So sine squared, and then I'll have 4x over 2. So now just applying the formula, I'll have sine 2x still, and then, yeah, the formula says 1/2 times 1 minus cosine of whatever we have up here. Okay, that's going to go down here, and that conveniently is 4x. All right, and just one last step, rearranging things a little bit to make it look exactly like what we have on the right-hand side. And that looks good. That is our right-hand side. So we have verified that the right-hand side and left-hand side are equal to each other. And the identity has been verified. All right, that's it. That's the last example for this section. Got a few more identities to see in 9.4, sum to product and product to sum formulas. So I will see you in that next section.